Hi everyone, let's continue with section 5.3 on solving trig equations, linear forms, where we don't have any squares or other powers on the trig functions. So let's solve secant of x minus root 2 equals 0. For a linear form, you generally want to isolate the trig function on one side. Let's add root 2 to both sides, and we get secant of x equals root 2. Now, you are allowed to take the reciprocal of both sides as long as they're not 0 and they're defined. Well, root 2 is a nice defined non-zero number. We can take the reciprocal of both sides. Be careful about doing this if you have more than one term on one side. But we have one term on the left, one term on the right. We can take the reciprocal of both sides. We get cosine of x equals 1 over root 2, or when we rationalize the denominator, root 2 over 2. And then you see I'm playing a trick on you. Cosine of x equals basically root 2 over 2. That's the same equation that we solved earlier. Really, we had a more complicated equation earlier, but it boiled down to this. So you have the same solution set. I'm playing games with you here. It's the same solution set. How about this here, though? Sine of x equals 2. In a way, that's another trick question. What's the solution set for that? Sine of x equals 2. What real values of x, what angles have the property that the sine of that angle equals 2? Empty set is the solution set. Because no real values will work here. 2 is not in the what of the sine function. 2 is not in the range of the sine function. So there are no real solutions for x. The solution set is the empty set. Next up, let's consider linear forms in tangent and cotangent. And why were these two different? What made tangent and cotangent different from the other trig functions, aside from their graphs, really? It was their period. So we tend to get more symmetry when we deal with equations with tangent and or cotangent. We're going to see that. For example, let's solve the equation tangent of x equals negative root 3. Now, is negative root 3 a tangent value? Is it in the range of tangent? Remember, tangent is very liberal. Tangent is slope. Any real number can be a slope, even positive a million, even negative a million. Any real number can be a slope, including negative root 3. And you might recognize that negative root 3 is a famous tangent value anyway. But here's the problem, though. We're more familiar with the case where tangent of x is positive root 3. So instead of finding the solutions to this right off the bat, let's find the reference angle for all the solutions. Find the reference angle for all the solutions. So I'd like to know where tangent of x is equal to positive root 3. Where's tangent of x equal to positive root 3? For some acute angle x. For some acute angle x. In other words, what's the inverse tangent of root 3? Well, let's see. Tangent is slope. Root 3 is about 1.7. That's a famous slope. It's pretty steep. What's the corresponding angle? Pi over 3, which was 60 degrees, by the way. Pi over 3 radians. Now, is that going to be a solution for our equation? No, because tangent of pi over 3 is positive root 3. So pi over 3 itself is not a solution. It's not itself a solution. Too much blue here. Let's go ahead and make this red. Or whatever that is, purple, not itself a solution, but it's the reference angle for all of our solutions. So it comes in very handy. It's the key brother for all the solutions, and that's going to help a lot. All of our solutions will have pi over 3 as the reference angle. That's really helpful. So now, in what two quadrants is the tangent value negative? In what two quadrants is the tangent value negative? Again, tangent is slope. Think of a decreasing line going through the origin. Tangent is negative in quadrants 2 and 4. In these two quadrants, tangent is negative. So this is very nice. I want all the angles with reference angle pi over 3 that lie in quadrants 2 or 4. I'm really in business. Who are they? Again, who are they? Think about it. Who are the brothers of pi over 3 in quadrants 2 and 4? Think of some famous ones. Actually, notice this. If you use symmetry, rotational symmetry, you only need to identify one brother. Let's go back to this unit circle. Where are the points I'm looking for? I'm looking for the point here. I want all the representatives for this point. And I want all the representatives for this point. I can take any of the representatives for either of these points. Basically, I can take any representative for any of these 2 points and go from there. I only have to identify one solution angle. The easiest one might be negative pi over 3. Although a good angle for this point here is 2 pi over 3, you could also pick that. But I don't need both. In terms of stating my solution set, I only have to identify one of them. I only need one representative for one of these points. Let's say negative pi over 3. And why is that the only angle I need to identify? I just have to identify one angle. So the solutions to the equation, tangent of x equals negative root 3, will correspond to this point and this point. Basically, the solution set consists of all the representatives for this point and all the representatives for this point. But here's how I can get them. I start with any representative for either of these 2 points. Let's say the negative pi over 3. I start with negative pi over 3. What can I add to get the 2 pi over 3 over here? Well, I'm rotating by half of a revolution counterclockwise. I can add pi to get to this point over here, and I get 2 pi over 3. And then I can add another pi. That is, I can add 2 pi total to get a coterminal angle over here. Add 3 pi, I'm back here. Add 4 pi, I'm here. Add 5 pi, here. Add 6 pi, here, and so forth. I can also subtract pi. If I take negative pi over 3 and I subtract pi, I'll get a coterminal angle for this, namely negative 4 pi over 3. Notice that if you had chosen 2 pi over 3 as the angle to focus on, if you subtract pi, you would have gotten negative pi over 3. So basically, I can take any representative for either point, and I add any integer multiple of pi, where n is any integer. Now, here's a simpler way to do it, although it takes more writing. I would accept this. You could say that the solution set is the set of all x in the reals such that x equals negative pi over 3 plus 2 pi n. So you grab a representative for this point and take all coterminal twins, or x equals 2 pi over 3 plus 2 pi n. So you grab a representative for this point and take all coterminal twins, where n is integer. I would accept that, but that's more writing than you need, as I just observed. You could just say that the solution set is this or this, the set of all x in the reals I'll write this better. It's technically optional, but it's good to write. The set of all x in the reals such that x is of the form, well, you could take the negative pi over 3 or the 2 pi over 3. You could take a rep for this point or a rep for this point. Plus pi n, where n is integer. So again, how can you sweep over all of the solutions in the solution set? Take any representative for either point, say the negative pi over 3, and add pi n, where n is any integer, 0, positive, or negative. If n equals 0, you stay here, negative pi over 3. If n is a positive integer, you're adding plus pi n, remember. If n is a positive integer, then you're going counterclockwise by half revolutions. If n is negative, you're going clockwise by half revolutions. But we're picking up all the solutions along the unit circle corresponding to this point and to this point. This is perhaps the most compact solution set, form for the solution set. And again, we could graph this. Y equals tangent of x, which of snakes. Y equals negative root 3, that horizontal line. Where do the green and purple graphs intersect? Let's see, over here at 2 pi over 3, look at that. Over here, negative pi over 3, look at that. And they're coterminal twins. All right. Again, you tend to get this pi n setup, plus this plus pi n deal when you're dealing with tangent and cotangent, because you have that different periodicity for tangent and cotangent. You often get this plus pi n type pattern for tangent and cotangent. Although sometimes you see it for sine and cosine as well. For example, if your solution set consists of all the reps for this point and this point, okay, well, your solution set is basically of the form pi n, where n is integer, and this is the solution set for the equation sine of x equals 0. So it's not just tangent and cotangent, but it's true that you often see plus pi n when you're dealing with equations in tangent and cotangent. But you also see that in other equations as well. Next up, what happens with quadratic forms and beyond? Next time.